Hi everyone. You may have come across the term inertial match while designing a drive system. But what exactly is inertial match and how is it going to help you design a drive system and how can you calculate it? That's what this video is about. So suppose we have this kind of a drive system in which we have an electrical motor over here, we have a load over here, and in between there is a transmission. And the transmission ratio is ROVB, and ROVB is defined as omega load divided by omega motor. And in general, ROVB is smaller than 1 in order to be able to drive a highly required torque required load by a smaller motor torque over here. And assume that the efficiency of this transmission is 100%, so it's really lossless. And now we are going to calculate the optimum transmission ratio in the case when the load is mainly dynamic. So we mainly have an acceleration torque. So in that case, the motor torque is an acceleration torque, which is the acceleration torque for accelerating the motor itself plus accelerating the load, and that acceleration torque calculated back to the motor level again. So my motor torque is equal to my acceleration torque is the acceleration torque of the motor plus the acceleration torque of the load calculated back, transformed back to the motor level. So when we work it out, we get T motor is the acceleration torque T ag, which is J motor, the inertia of the motor, times the angular acceleration of the motor, which is the derivative of the angular speed of the motor, the omega motor dt, plus the acceleration torque of the load, which is J load times the omega load dt, which is the angular acceleration of the load. So it's the derivative of the angular speed of the load. And we have to transform that load back to the motor level by multiplying this by ROVB. Well, when we now replace omega motor by using this definition, so replacing omega motor by omega load divided by ROVB, we get the following expression. T motor is T acceleration, and at this point over here we fill in not omega motor but omega load divided by ROVB, and then we get the expression J motor times the derivative of omega load divided by R of B plus this expression again, which was R of B times J load times the omega load dt, so the angular acceleration of the load. So you see now that we have in both terms of this expression, we have the angular acceleration of the load. So we can take these two parts together and multiply the summation of it by the acceleration of the load. And when we do that, we get T motor as T acceleration, which is equal to J motor divided by R over B, this part, times the angular acceleration of the load, this part, plus R of B times J load, which is standing over here, times the angular acceleration of the load, which is standing over here. And you can see that this is correct because when you multiply this part by that part, you get this part of the expression. And when you multiply this part by that part, you get this part of the expression. So this is it. And the last thing we can do is we can replace d omega load dt, so the angular acceleration of the load, by alpha load, and then we get this expression. So this is an expression of the motor torque, which is equal to an acceleration torque. And remember, it's the acceleration torque of the motor and the reduced acceleration torque of the load. So now let's have a look how we can choose in this dynamic situation a value for ROVB in a way that the motor torque is at the lowest version. So we want to have the minimum motor torque and we have to choose the ROVB meeting that minimum motor torque. So we are looking to a local minimum of this function, and we can get that by taking the derivative of the motor torque towards the transmission ratio R over B over here and set that to 0. So when we do that, so we take the derivative of the motor torque towards the derivative of ROVB and set that to 0, and we work that out, we get the optimal ROVB in order to get the lowest motor torque. And when you work that out, you see that ROVB, the transmission ratio, is equal to the square root of J motor divided by J load. So again, when you choose this value for your transmission ratio, then you have in a dynamic situation the lowest motor torque needed. So that is what we call inertial match. Okay, so what is in this situation, in this example, the inertia, complete inertia at motor level? Well, that is the motor inertia itself plus the reduced load inertia towards motor level. So it's J motor plus J load star, which indicates the reduced inertia from the load towards the motor shaft. And you should know that when you transform an inertia of a load towards motor level, you have to multiply it with the ROVB squared. And when you do that, you find the expression that J in total is equal to J motor plus the reduced load inertia, which is equal to J load times ROVB squared. So that is in general in this kind of a system. Now let's look what happens when we choose for the ROVB the inertial match value. So replace ROVB by the square root of J motor over J load. And in that case, we see that the total inertia at motor level is equal to J motor plus, we fill in this expression over here for REVB, and then we get that expression. And when you work that out, you see that the total inertia at motor level is equal to 2 times J motor when using the inertial match expression. So again, the optimal ROVB for defining the lowest motor torque is using this as a transfer ratio square root of J motor divided by J load. So in that case, the torque we require is at the minimum value, which is also good for the current because we need less current in that case, and also the copper losses, which is E squared times R, is also at the lowest value. So it's very good to use this as a value. But now let's look to a real case. And in that real case, I want to show you if this expression is really that stringent as what we calculate over here. So what we do over here is I've made a drawing over here in which ROVB is my variable, and at every RFB value, I calculate the motor torque. And on a horizontal axis, I've put 1 over ROVB, so this is a transmission with a transmission ratio of 1 over 10, and this one 1 over 20, this one is 1 over 30, etc. And when you calculate the motor torque for all of these values, you see this as a curve. And also in this situation, I've put the load of my system to 0. So there's no friction in it, there's no constant load to it, etc. There's only acceleration load. And we see that when you calculate the optimal ROVB using the inertial match calculation, we see that the ROVB is equal to almost 0.1, so 1 over the ROVB is almost 10. And that is also what we see in this graph. Well, at a transmission ratio of 1 over 10, well, this motor torque is at its lowest value. But what we also see is that it doesn't matter that much if your transmission ratio is 1 over 10 or 1 over 9 or 1 over 11 because, well, in this range, the motor torque which you need is still very low. So inertial match is a good starting point for your calculation, but it's not the holy grail. It's not that when you don't match your inertial match definition, you have a really huge motor torque because somewhere in this area you still have a low motor torque value. What we also can do is we put in a high value for the load torque, see what happens over then. So in that case, we don't have a dynamic load anymore, but a dynamic load with a static load. And when we do that, for instance, we fill in 100 Newton meter over here, we see, well, that at a certain transmission ratio, it doesn't matter that much what your transmission ratio will be because your motor torque is still low. So you have to cross a certain value somewhere over here in this example, like let's say 1 over 13 or 1 over 14, and after that value, your motor torque is still very low. You can also calculate the minimum value of this curve, and you can do it the same way as we did when calculating inertial match, but then you have to take into account that static motor torque over here, which is the load torque multiplied by R over V. So when you take that into account and then take the derivative of the motor torque towards the R over V, and you look at you calculate the lowest value, so we set this derivative to 0. You see that the optimum R over B, when taking a load torque into account, that optimal R over B is equal to the square root of J motor times alpha load divided by J load times alpha load plus T load. Again, when T load is 0, then this part is 0 in the expression, and then this leaves us with this expression over here in which we can get rid of alpha load, which brings us to the optimal R over B, which meets the inertial match definition, which was square root of J motor over J load. Well, that's all with respect to inertial match. I hope you enjoyed the video, and I'll see you next time. Bye bye.